morning. I welcome you all to this session of fluid mechanics. Today we will start a new chapter, that is flow of ideal fluids. We will describe here a brief discussion on the flow of ideal fluids. Now, what is an ideal fluid? We have already recognized the definition. An ideal fluid is a fluid which has no viscosity, and therefore flow of such fluids known as inviscid fluids which has no viscosity is known as ideal flow. In addition to this non-viscous nature of the fluid, that means zero viscosity, we will impose here two other properties of the fluid, that incompressible, that density remains constant, and at the same time irrotational, the rotation in the flow of fluid is zero. So therefore we will mainly discuss the flow of an ideal fluid with incompressibility. Ideal incompressible, that means inviscid, incompressible and irrotational flow. So let us recall few of the corollaries of the incompressibility and irrotationality in a flow field. Okay. Let us concentrate our analysis on a two-dimensional frame of reference. Let us take a two-dimensional x and y in a Cartesian coordinate system. We consider a two-dimensional flow in a Cartesian coordinate system described by x and y axis. Now in this case we know that an incompressible flow, for an incompressible flow, the equation of continuity, conservation of mass, for an incompressible flow is del u del x plus del v del y is 0, where u and v is the velocity in the x direction and y direction. That means velocity vector v has the component u and v in along x and y axis respectively. Now as a consequence of this continuity equation, we define a function, stream function. We have discussed in details about this earlier. Stream function psi, which is a function of space coordinates xy in such a way that the velocity components are defined like this: u is del psi del y and v is minus del psi del x. One is positive, another is negative, so that the psi function, that is the stream function, automatically satisfies the continuity. You see that if we substitute u and v from this definition, we get that this automatically becomes 0. That means stream function automatically satisfies the continuity. This we have already recognized earlier. Now you see that we know that for a streamline, the stream function psi remains constant along the line. Now if we recall the definition of a streamline definition, we know that the tangent to it at any point represents the velocity vector, and the equation of a streamline is that dy dx in a two-dimensional frame is equal to v by u, because the slope of this streamline gives the direction of the velocity vector. So for a two-dimensional case it is like this, which gives the u dy minus v dx is equal to 0. This is nothing but the equation of a streamline. Now let us see that if we expand psi in a differential form, we can write d psi, psi being a function of both x and y, we can write del psi del x dx plus del psi del y dy. Now del psi del x by definition is v minus v, and del psi del y by definition is u dy. Since the equation of a streamline, that means along a streamline u dy minus v dx is 0, so d psi is 0. So along a streamline d psi is 0, that means psi is equal to constant. So therefore we know that the streamlines, for example, if these be the streamlines at any instant, in a steady state the streamlines remain same at all instant of time. So psi is equal to constant, that is psi 1, let this is psi 2, let this is psi 3. That means we can ascribe a single value of psi for each and every point along a streamline. So this we have discussed earlier. Now if the flow is irrotational, now in a two irrotational flow means we have discussed earlier, that is a flow where rotation is 0. So rotation has got three components along the three axis, coordinate axis. Now in a two-dimensional flow there is only one component of rotation, that is the rotation about the z axis. How do you define rotation? We defined it earlier that rotation is the arithmetic average of the angular velocity of two linear segments which were initially perpendicular to each other. That means if we take a point P and AP and BP are the two linear segments mutually perpendicular to each other, then because of the flow field, this tendency of rotation of these linear elements in the opposite direction, for example, if we take the arithmetic average of the angular velocities of these two linear elements, we get the rotational component, and we have already derived earlier this with respect to z axis. That means an axis perpendicular to the plane of this figure. That means at P the axis is perpendicular to the parallel to a z axis here, which can be represented like this. It will be half del V del x minus del U del y. Now we can recognize the other component of the rotation. That means x. That means in yz plane, rotation in yz plane. This is rotation in xy plane, that is rotation about z axis. Rotation in yz plane, that is about x axis. Rotation like this, it will be y and z. That means del w del y minus del v del z. Rotation in about x axis, that is omega x, del w del y minus del v del z. Similarly, with respect to y, it will be del u del z minus del y it is, that means del w del x, del u del z minus del w. So three rotational components. And for an irrotational flow, all these three components become independently zero. For a two-dimensional case, we don't come across this defined in an xy plane, so rotation is only this, so this becomes zero. So these three together is written in the form, if you recollect, is 0, where v bar is the velocity vector, which has got three distinct components, u, v and w. Now for an irrotational flow, del v del x minus del u del y is 0, or we can tell that curl of velocity vector is 0. Now a consequence of this mathematical relationship is that this vector v can be expressed as a gradient of a scalar function phi. So this is a mathematical theorem that if curl of any vector is 0, that vector can be obtained or can be expressed as a gradient of a scalar function. So this scalar function phi is known as the potential function. If this vector is the velocity vector, in case of irrotational flow, curl of this velocity vector is 0, then velocity vector can be obtained as a gradient of the scalar function phi, which is known as velocity potential function. Velocity potential function, or simply velocity potential. Now a negative sign is deliberately used to make the thing similar to all phenomenological equations where any flux is proportional to the negative gradient of the potential function. So therefore a negative sign is implied. So for that, if you just expand this, then we can write for three-dimensional cases with respect to a Cartesian coordinate system. Simply we can write u is equal to minus del phi del x, v is equal to minus del phi del y, and w is equal to minus del phi del z. So for a two-dimensional case, we can deal with these two. U is equal to minus del phi del x, v is equal to minus del phi del y. And the curve or the line along which phi remains constant is known as equipotential line. Is known as equipotential line. Equipotential line. Now let us find out the equation of equipotential line. The equation of equipotential line means phi is equal to constant. This is the equation. But we try to derive it in terms of u and v. What to do? You write it in a differential form, that d phi is 0. Now what is d phi? D phi is, because phi is a function of x and y. This is a scalar function, point coordinate x and y in case of two-dimensional system. In three-dimensional flow, it is a function of x, y and z. So it is del phi del x dx plus del phi del y dy, and that must be equal to 0 along a equipotential line. So del phi del x is minus u, del phi del y is minus v. So therefore we see u dx plus v dy is 0. So this is the equation of equipotential line. Equation of equipotential line. Equation of equipotential line. Similarly, equation of streamline is v dx minus u dy is 0. This is the equation of streamline. This is the equation of streamline. So immediate inspection of these two equations said that they are mutually orthogonal. They are perpendicular to each other. U dx plus V dy is 0 and it is V dx minus U dy is 0. The slope of this line at any point and slope of this line at any point are perpendicular to each other. So therefore, we can say that if these be the streamlines, these be the constant streamlines, psi 1, psi 2, psi 3, psi 4, then the orthogonal families of curves will be the constant phi lines. So they will be, these corners will be 90 degree. So they mutually form a orthogonal sets of trajectories. So this is constant psi line, these are the constant phi lines. Now we come to the concept of circulation. What is meant by circulation? What is meant by circulation? Let us consider in a flow field a closed loop and bounded by a closed contour. Now if we designate some small elemental length as ds, where the velocity vector is v bar, then the contour integral of this v dot, let us define a vector, normal unit vector along the tangent to this, that means along the tangent to the curve at this point, that means along the direction of this linear element ds, and unit vector n1 we define, then n1 ds, which means that the elemental ds is given a vector concept by multiplying it with a unit vector along the elemental length, that means along the tangent to that length. Then this quantity, if we make a contour integral over this closed contour, then we define this as the circulation, gamma, which is the symbol. So gamma is the circulation. Circulation. It simply means that the length, linear elemental length multiplied by the component of the velocity along that length. So velocity vector may have in any direction component of the velocity vector along that length, and if we sum up all such quantities, product of the velocity component along a linear, along a infinite small elemental length, and product of the length times the velocity component along that direction, and sum it up over a closed contour, then this is known as circulation around that closed contour or closed circuit. This is known as circulation. Okay. Now we can show that the circulation for any closed contour can be found out by the circulation of small grids or small contours generated within that big contour, closed contour. That means, for example, if this closed contour is now divided into a number of small circuits, this big circuit is divided into a number of small circuits, and you see that if we have the velocity component like this, now what happens? Before that I must say that when we make this integral, we take certain direction for this integral along the closed contour. If we make in this direction, usually taken as positive conventionally, so this is given a direction like that, a contour integral or a closed contour integral along a closed contour is given with a sign, so this is positive along this sign. That means conventionally taken the anti-clockwise direction, or rather this way you take an anti-clockwise direction. This is not anti-clockwise, so this is an anti-clockwise direction. Let us consider the anti-clockwise direction. That means this direction, anti-clockwise direction, as a positive. Now you see, therefore, for a small circuit, the circulation will be defined the velocity vector multiplied by this length, velocity vector multiplied by this length, this velocity vector multiplied by this length, this velocity vector multiplied by this length. Now you consider the common edges. That means this edge, the contribution of the velocity at this edge in the circulation for this grid is in one direction, and for this grid is in other direction. So for all these common surface, it is like that. It contributes in the calculation of circulation for one grid, one closed circuit in one direction and another adjacent closed circuit in another direction, so that they ultimately nullify each other or cancel each other, and we are left only with these contributions along the outermost boundary. So that ultimately if we sum up the circulations of these infinite small circuits, we get the circulation around the closed circuit. Now let us find out the circulation in case of a xy coordinate. Let us see a simple case. Consider a circuit. We can choose a circuit, a rectangular circuit like this, of length dx and length dy. What will be the circulation? Let us consider at this plane the velocity is u, and at this plane the velocity will be changed for a distance dy will be u plus del u del y dy. Similarly, let us consider the velocity at this plane will be v, positive direction. So velocity at this plane will be changed for a distance dx as v plus del v del x dx. Now let us find out the circulation with the anti-clockwise direction as the positive direction. Now what is this? This will be u for this length, this elemental length, u into dx, and this has got an anti-clockwise rotation about any point within the circuit. This is the way the direction for the rotation has to be taken care of. Similarly, for this element, it is the velocity along this element is v plus del v del x dx. U doesn't have any component for this which is perpendicular to this linear element. So therefore, it is the velocity component along the linear element times dy. This gives also in the same directional notation. So plus v plus del v del x dx times dy. Then for this, it is an opposite direction, but the magnitude is this velocity component times the length dx. That means minus u plus del u del y dy. This is the velocity component times dx. Minus this one in the same direction, that means minus v times this length dy. So if you make it simple, so it will become ultimately del v del x minus del u del y into dx dy. This is because you see v dy cancels, u dx minus u dx cancels. But this is our twice the rotation, and this is, you know, is the vorticity about the z axis. We earlier defined vorticity is the 2 times the rotation vector. If you represent vorticity as a vector, then it is 2 times the rotation vector. So this is the vorticity, so vorticity times dx dy. What is dx dy? Dx dy is the area of this contour. So we can tell that circulation divided by this area is the vorticity. Alright, this is vorticity. So this is a very important theorem from which we can write that vorticity is equal to, very important theorem, vorticity is equal to, over a closed circuit or loop in a flow field of an irrotational flow, ideal, that is inviscid, incompressible and irrotational flow, circulation divided by area. So this can be expressed in a general way by the application of Stokes theorem. This is known as Stokes theorem for ideal fluid flow, but Stokes theorem in general for mathematics tells in this fashion, that if there is a closed path, closed area, it is bounded by a closed surface S, and if the area is A, and if a vector P is defined throughout this domain, continuous vector space, then Stokes theorem tells that vorticity times the area is the circulation. Stokes theorem states that curl of this, if you consider a small area dA, okay, and if you consider some, for example, n2 vector which is perpendicular unit vector in a direction perpendicular to the area, then dot n2 dA is the closed contour with any direction as the positive, anti-clockwise is usually positive, into this vector p dot e dot n1 ds, where ds is a small elemental length, and n1 is the vector, unit vector, as I have told earlier, along the tangent to this line, along the tangent to this line. So this is the Stokes theorem which relates the, this is over the surface A, this is over the contour S, which relates the line integral with the surface integral. You have read in mathematics probably. So this Stokes theorem, when vector P in general takes the velocity vector in case of an ideal flow, gives the Stokes theorem as an ideal flow, then this left hand side becomes the vorticity and this is circulation. So vorticity is circulation per unit area. Now after this I will give you the concept of flow nets. Concept of flow nets. What is flow net? Concept of flow nets. Now flow nets are that in a flow field we have seen that psi is equal to constant line, that is streamlines, and phi is equal to constant line, that are equipotential lines, are orthogonal. So a series of such lines in a flow field comprises a flow net. A flow net. That means let this is psi plus 2 del psi with an interval of delta psi if I draw the if I draw the streamline, the constant psi lines, that is 5 lines I draw, for example 4 lines, psi plus 2 delta psi, it will be psi plus delta psi, it will be 2 delta psi, it will be 3 delta psi, it will be 4 delta psi. So with an interval of delta psi I draw it. Similarly, if I draw the equipotential line which are orthogonal to this set phi, this line is phi plus delta phi, then this line phi plus 2 delta phi, then similarly phi plus 3 delta phi, phi plus 4 delta phi, then these two sets of lines form a mesh, a network of such closed meshes. So these are known as flow nets. This entire network is known as flow net. This gives a quadrilateral whose angles are 90 degrees. Now in a special case when del psi is equal to del phi is equal to some del s and del s tends to 0, that means psi and phi lines are very close to each other, this goes to a perfect square. Now certain things are obvious from the qualitative picture of this. Now for example, you know that u is equal to del psi del y, v is equal to minus del psi del x. Similarly, u is equal to minus del phi del x, v is equal to minus del phi del y. So you see the closeness of the psi lines and also phi lines represents the fluid at higher velocity flow. Higher velocity flow in a flow field where velocities are high. So for example here these psi lines will be very close. That means if u is high, for a given delta psi, delta y will be less, or for a given delta y, delta psi will be high. That means for a high velocity the psi lines will be close together. Similarly phi will be. For example here if we define the velocity component, for example we have to find out the difference. For example here the velocity component here in this direction is the difference between this psi function and this psi function divided by this length, then delta psi divided by this length. Similarly to define the potential from the potential potential phi, constant phi lines, this is the difference between these phi lines and these phi lines divided by this distance. So therefore you see we can very well find out that the closeness of the psi and closeness of the phi will indicate that velocity is very high. Again I am telling the velocity component here will be found out as del psi del y. For example that this psi function minus this psi function divided by this length, because it is normal to the velocity vector. Whereas in terms of phi, this value of phi lines, the value of phi along these lines, value of phi along this line divided by this length, in this case this length. Okay. So therefore we can construct flow nets in such situations. So another type of flow net, for example if the xy, if the streamlines are along the x-axis, so then this will be the flow net. For example xy, this will be the flow net, structure of the flow net, if the with a similar interval, and if this be the, so obviously in that case the phi lines will be the perpendicular lines along the y-axis. So this will correspond to. These are phi is equal to constant lines. The vertical lines are phi is equal to constant lines, and similarly the horizontal lines are psi is equal to constant line. So typical square with del psi and del phi remaining same, that this and this, so that this gives a flow net for a flow field where the fluid velocities are along the direction of the x-axis. So streamlines are parallel to the x-axis. So this is the concept of flow net. Now I will tell you one thing, that with the definition of psi and phi function, you must know one very important thing, that we have defined that for an incompressible flow, incompressible and irrotational flow, that for an incompressible, now the question comes like this, for an incompressible and irrotational flow. Now for an incompressible flow, the psi function exists, incompressible two-dimensional flow. So existence of psi function comes from an incompressible two-dimensional flow. That means the function automatically satisfies the continuity equation. Similarly, if the flow is irrotational, then the existence of potential function comes. So if flow is not irrotational, this function will not come. If the flow is not incompressible, the psi function will not come. Now if the flow is both incompressible and irrotational, then what happens? Due to incompressibility, the psi function exists. It is the consequence of incompressibility. So if I substitute the psi function in the condition of irrotationality, what we get? Del v del x minus del u del y. It is not satisfying automatically because it is a consequence of incompressibility, not of irrotationality. So if we substitute this psi, you recall that u is equal to del psi del y and v is equal to minus del psi del x. So if you substitute this, you get del square psi is equal to 0. That means del square psi del x square plus del square psi del y square is 0. That means the Laplacian, this is known as Laplacian. You know that this operator in a two-dimensional case, del square, this is known as Laplacian, vector operator, Laplacian. Laplacian psi is 0. So therefore psi satisfies the Laplace equation in case of an irrotational. Similarly, if we see that due to the irrotationality, phi function exists. That means phi function is a consequence of irrotationality. So if simultaneously fluid is incompressible, what equation does this phi function satisfy? That means irrotational incompressible flow equation means if you use the equation of continuity, for which psi satisfies automatically but not phi. Phi originates from this, phi satisfied automatically this equation. Now if you substitute this phi in terms of phi, with the definition is that u is minus del phi del x and v is equal to del phi minus del phi del y. We get the same equation, same type of equation, not the same equation, del square phi del x square plus del square phi del. That means Laplacian phi is 0. So therefore, for an incompressible and irrotational flow, the psi function satisfies the Laplace equation and phi function also satisfies. So to evaluate the psi function and phi function, we have to solve only the Laplacian psi is equal to 0 and Laplacian phi is equal to 0 with requisite boundary conditions. Okay, now after this, I will discuss certain basic flows. First, we discuss rectilinear flow. Rectilinear flows are flows in straight line and the velocity vectors are parallel to each other. That means if we define it in terms of a two-dimensional Cartesian coordinate system, most generalized type of rectilinear flow is that along a straight line parallel to each other, the velocity vector is like this. Sorry, that is the velocity vector. This makes an angle alpha with the x-axis. So the velocity vector can be written as u plus v. So uv is the component along x and y axis. So where u is equal to v sin cos alpha and v is equal to v sin alpha. Now how to draw the streamlines or stream function and velocity potential, evaluate the stream function and velocity potential function? Very simple. So u is equal to del psi del y. That means del psi del y and v is equal to minus del psi del x. So del psi del y is u. What is u? V cos alpha, or I can write simply u, which is constant. In case of rectilinear flow, v is constant along a straight line. So similarly, del psi del x is minus v. So if you integrate these two partial differential equations, so you get from here psi is equal to uy plus function of x plus some constant c1, and phi is equal to minus v, I am sorry, it is u into y after a minus vx plus function of y plus c2. Comparing these two, this is psi, sorry, comparing these two, psi is equal to uy minus vx. So this will not occur, function of x will be this, function of y will be this, plus some constant. So this is the equation of the streamline. So if you want to find out the equation of the velocity potential, in the similar way we write that del phi del x is minus u and del phi del y is minus v, and if we integrate it, we phi is minus ux minus vy plus another c. Let this is c, this is c dash. So therefore we see that two equations, uy minus vx plus c, and we get phi is equal to minus ux minus vy plus c dash. So these are the two equations for streamline. Now in a special case, for example, if the v component is 0, so velocity is only in the x-axis, along the x-axis psi is simply uy plus c, and this phi is simply, in that case, if v is 0, minus ux plus c dash. That means a constant psi line in that case will be uy plus c is constant. That means in one word y is equal to constant, and a constant phi line will be minus ux plus c dash is constant, or in other way x is equal to constant. That means a constant phi streamlines are the lines parallel to x-axis because y is constant. So c may be made 0 if I define psi is equal to 0 at y is equal to 0. I can define the value of psi 0 at any arbitrary location because it is the difference in psi which is most important to find the velocity, because we are finding out the velocity in terms of the difference in psi. That means I can define this psi along the x-axis, that means coinciding the x-axis itself is the line psi is equal to 0 for this flow. So therefore this is psi 1, psi 2 parallel, psi 3, psi 4. Similarly, x is equal to constant and phi is equal to 0, I can define the y-axis as phi 0, and all lines parallel to y-axis are different phi 1, or different phi 1, phi 2, phi 3, phi 4. So this way we can find out the psi and phi function. All right. Now we come to the another type of flow, that is source and sink. What is a concept of source, which is very important. We have already defined the vortex flows, so I am not going to repeat the vortex flows, the free vortex and forced vortex flows which constitute the flow of ideal fluids. Now source and sink. Now source and sink. First of all, source and sink. Source and sink. Now source is defined like that. In a two-dimensional flow, source is like this, from a point where the source flow is like this, where the streamlines are coming out radially. That means the flows are coming out radially and uniformly in all directions. Then streamlines are radial lines with uniform spacing. This is the concept of source, wherefrom the fluid is emanating in all radial directions uniformly. So that is the concept of source, and in a two-dimensional concept I can write, or we can write, a line source. That means in a two-dimensional plane it is a line source. That means it is a line perpendicular to the plane of the figure, which is seen as a point in a two-dimensional plane end on. That if a line is there perpendicular to this plane, then this line seen end on will give a point P, which is the point source from where the fluid is emanating radially outwards uniformly. So this is the basic definition of a source, and sink is just reverse of this source. That means where fluid is approaching or coming towards that point uniformly from all radial directions. That is the sink. That is the negative version of the source. Now for a line source, the strength of the source is defined as, so a terminology is known as strength of the source, strength M usually. So strength, sometimes M, sometimes we can define as gamma. Okay, let us define as M, the strength. It is nothing but the mass flow rate coming out from the source. Now what is the mass flow rate? Mass flow rate coming out per unit length in case of two-dimensional flow, if you consider a linear element perpendicular to this plane, per unit length will be the density of the fluid times twice pi r at any radial location r, twice pi r. So this is simply the definition of the mass flow rate. In terms of mass flow rate, M is equal to rho twice pi r. So all right, so therefore we can define the strength of the source as the mass flow rate, which is twice pi r times an unit length times the radius. So this is the flow area, and this is rho into VR into VR. That means twice pi r into unit length is the surface area times the VR times the rho. This is the mass flow rate. So this is the M is this known as strength of this. Now you find out the expression for stream function psi. Now here, as the fluid is coming in all radial directions uniformly, it is better to adopt a polar coordinate system, that a point here by giving r as the radial coordinate and theta as the azimuthal angle, and we consider any arbitrary reference line as theta is equal to 0 from where the azimuthal angle theta is measured. So if you recall the definition, and if we consider the Vr is the radial direction velocity and V theta is the azimuthal direction velocity, then if you recall the stream function in terms of the Vr V theta is equal to, Vr is 1 by r, similar way we have done for a xy coordinates or Cartesian coordinate, V theta is minus del psi del r. All right. So these are the definitions of Vr V theta. So from here we can see that for a source, by definition V theta is 0. Okay. So therefore this is 0, which means psi is not a function of r, del psi del r is 0. So therefore psi is a function of theta only. So we can change this partial derivative to a ordinary differential form, that means a total derivative d psi d theta is Vr. Now Vr in terms of the strength of the source, that is mass flow rate, which remains constant in the flow field, M by twice pi rho 2 pi rho r. So that is the Vr. So if you multiply it, so r cancels, we get psi is equal to M by 2 pi theta plus constant c. All right, C1 for example. So therefore a constant psi line, psi is equal to constant, if I put, we will give M by 2 pi theta plus C1 is constant, that means theta is equal to constant. That means along a constant psi line, theta is constant. That means these are the radial lines. So therefore the psi lines, constant psi lines are the radial lines. Theta is equal to constant. And this is the expression for the psi, stream function psi. Okay. If I consider that theta is equal to 0, psi is equal to 0, then C1 is equal to 0, psi is equal to M by 2 pi theta. And accordingly we can ascribe the values of psi for different thetas. So, well, now if I find out the values of phi in this case, what we will see the values of phi in this case will be, phi is equal to, I can write Vr is minus del phi del r, and V theta is 1 by r del phi del theta. And if you make that definition that V theta is 0 for a source flow, so this is 0. So phi is not a function of theta, phi is a function of r. So therefore I can write del phi del r is minus Vr. Again Vr is minus, you remember that Vr is M by rho twice pi r. M by twice pi rho r. If you just integrate it, it will be like this, M by twice pi minus ln r by c. We just induce some constant, so m by 2 pi ln r by c. So this is the expression for velocity potential function. So phi is equal to constant lines, constant line will be the line along which this is equal to constant, which means ln r by c constant, which means r is equal to constant. So r is equal to constant lines will be the phi lines. That means phi lines will be the concentric circles. And obviously we have already recognized that psi lines and phi lines will form orthogonal families of curves. So if the radial lines are the psi lines, so concentric circles will be the constant phi lines. So this is the expression of potential function, velocity potential function, and this is the expression for a stream function in case of a source. For a sink, it will be just the reverse. So with a negative sign, these expressions will show the expressions for stream functions and the velocity potential functions for a sink. Qualitative picture will remain the same. Okay, thank you. Good morning. I welcome you all to this session of fluid mechanics. Today we will be continuing the discussion on ideal fluids, the ideal fluids part 2. Now last class, if you recall, we discussed about the stream functions and the velocity potential functions and the stream lines and the velocity potential lines, equipotential lines for source and sink flow. If you recall that, now we can see here that a source flow is a flow which in a two-dimensional plane can be thought of as a line source, which is seen end on as a point where from the fluid is coming out uniformly in all radial location. This is a source, and sink is the reverse of this, where the fluid is approaching towards a point uniformly from all radial directions. All right. So in this kind of flow, we derived earlier the stream function was given by m, where m is the strength of the source, which is the mass flow rate, total mass flow rate coming out from this source, by twice pi rho into theta with a minus sign, and the velocity potential function was recognized as m by twice pi rho ln r by r0. All right. So where this r0, so therefore first of all let us see that the constant psi lines, that is the stream lines, is psi is equal to constant where theta is constant, that means the radial lines. So radial lines are the stream lines. Similarly, equipotential lines are the lines where r is constant, if you make phi is equal to constant. So these are concentric circles. And r0 implies a radius where we have considered an arbitrary value of 0 for the phi function. Now for a sink, this is for a source. So for a sink, the stream function for sink is just with a negative sign, because source and sink are physically same, only with a negative sign. Similarly, phi for a sink will be, that velocity potential function for a sink will be like this. Now today we will see the superimposition of certain basic flows. Now superimposition, let me write superimposition of basic flows, superimposition of basic flows. Now one thing you must know, that when two flow fields are superimposed, if the velocity vector of one flow field is v1 and the velocity vector of another flow field is v2, that means v1 and v2 are the velocity field of the two flows which are superimposed with one another, then the velocity vector, the resultant velocity of the flow field will be the vector addition of these two velocity vectors. Since psi is a linear function of the velocity vector, then if psi1 represents the stream function for one flow and psi2 for another flow, then the resulting flow will have a psi function or a stream function of the stream function of the resulting flow will be the sum of the stream functions of two flows. This is because stream function is a first order derivative of, not first order, rather I will tell first power, bears a first power relationship with the velocities, because it is simply the derivative of the velocities, velocity gradient. So therefore, the basic conclusion is that if psi 1 is the stream function for one flow and psi 2 is the stream function for other flow, if these two flows are superimposed, the resultant flow psi function can be obtained by the addition of the psi functions of these two. Now with this method, with this basis, we can now see first the combination of source and sink. Source and sink, combination of source and sink. Now let us consider a flow where a sink, source and sink located like that. Let A is the source and B is the sink. A is the source, B is the sink. Now if we consider a point P in the flow field which is generated by the combination of source and sink, now we can write like this, that if we just join these 2 points, let this is theta 1, theta 2. In a polar coordinate system, we can write that for source, this psi, that is psi 1, that is psi A, is minus m by 2 pi rho, all right, theta 1. Now for the sink at B, psi B is equal to negative of that, so therefore it will be twice pi rho theta 2. So therefore we see the psi function for the resulting flow, that is the flow which results in due to the combination of the source and sink, will be psi A plus psi B, which can be written as m by 2 pi rho into theta 2 minus theta 1. All right. So this theta 2 minus theta 1 from geometry is this angle. So therefore we see psi is equal to theta, where theta is the angle APB, where theta is angle APB. Now here we see one interesting thing, that the constant psi function lines, that means streamlines, are those lines along which theta is constant. Because if we put psi is equal to constant, which will give theta is constant, which means these will be the circular arcs, that means the streamlines will be the circular arcs with AB as the base chord, so that this angle will always remain constant. That means this will be the this will be the, for example, this is one circle whose chord is AB. So this is source, this is sink, so this will be the streamlines. So other circular arcs can be thought of these streamlines like this. Now we can develop the expression for stream function in a Cartesian coordinate system. Let us consider this x, let us consider the y axis. Let the coordinate of any point is xy. Then therefore we can write tan, this theta 1 and theta 2 is there. Now we can write tan theta 1 is what? Y, the y coordinate of the point, divided by b plus x, b plus x, where we take this distance as b. That means the coordinate of A, where the source is kept, is minus b0, and the coordinate of B on the positive x-axis, where the sink is kept, is b0, which means if this be the origin, OA is equal to b, OB is equal to b, so b plus x. Similarly, tan theta 2 is equal to, theta 2 is this angle, we drop a perpendicular from the point P on the axis, we will get y is into x plus b. I am sorry, x minus b. X, this is x minus b. It is x plus b, it is x minus b. All right. So therefore we can write tan theta 1 minus theta 2, which is equal to, you know the formula for this, tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 tan theta 2. So therefore we can write tan theta 1 minus theta 2 is equal to, if you replace this, y x plus b minus y x minus b divided by 1 plus y x plus b into y x minus b. So if you simplify it, it will come 2by divided by x square plus y square minus b square. So therefore, we can write with this that the psi, okay, here we can write, therefore psi is m by 2 pi rho theta 2 minus theta 1. So, well, it is theta 2, I am sorry, we will have to make it theta 2 minus theta 1. So, theta 2 is x plus b. So, theta 2 is x plus, theta 2 is x minus b, it is x plus b. So, this is all right. So, it has to be theta 2 minus theta 1. I am sorry, theta 2 minus. So, if you see that theta 2 minus theta 1 is tan inverse this, that means tan inverse x square plus y square minus b square. So, therefore, in Cartesian coordinate we get the stream function psi is equal to m by 2 pi rho tan inverse in terms of the Cartesian coordinates 2by x square plus y square minus b square, where 2b is the distance between the source and the sink, m is the strength of both the source and the sink. Now we will consider a case where source and sink are placed such a way that the distance between them tends to 0, with the condition that the strength times the distance remains finite or constant. That means the source and strength are kept at a distance and ultimately they are approaching towards each other, the distance between them tending to 0, with the constraining equation that the product of the strength and the distance of separation is constant. So, this type, the flow field which is arrived is known as doublet or dipole. The flow field which is arrived by this way, combining source and sink in this way, is known as a dipole. So, what we can do, this is the combined stream function for a combination of source and sink. From here we can see that if 2b tends to 0, that means this tends to 0. So, tan inverse of a quantity which is tending to 0 can be written as the quantity itself, which means that tan inverse x at x tending to 0 is equal to x itself. So, therefore, we can write under that limiting conditions for a doublet or dipole, psi is equal to m by 2 pi rho with this mathematics into 2by divided by x square plus y square minus b square. So, limit of this as b tends to 0. Now, when b tends to 0, but bm is constant, so that we can write bm by pi rho, cancelling these 2, bm by pi rho into y, b tending to 0, that means y by x square plus y square. Or simply we can write in terms of polar coordinate bm by pi rho into r sin theta divided by r square. Considering these as a constant c, we defined a constant c as bm by pi rho, because bm is constant according to the definition of this type of problem. So, therefore, we can write c sin theta divided by r. This is the stream function of a dipole. So, dipole will be like that. When you see this source and sink will approach each other, this angle will become 0, and ultimately these circular arcs with AB as the base chord will become tangent, will become circles with tangent at the x axis at the origin. That means this will be the nature of the this will be the nature of the this will be the nature of this. Now, okay, this will be the nature of this dipole, where dipole is at the origin, because they are placed symmetrically up from the origin and they are tending to the distance of separation tending to 0. This is the dipole or doublet, streamlines of the dipole or doublet, constant stream functions. Now we will come to a very interesting phenomena or very interesting situation by superimposition of rectilinear flow, which we have discussed earlier, rectilinear flow and doublet doublet. Now, the superimposition of these two flow gives the stream function for the resultant flow, which is the sum of the stream functions for rectilinear flow and that of doublet. Rectilinear flow, if you recall, the stream function is given by uy, where u is the velocity of the rectilinear flow, but here rectilinear flow parallel to x-axis. So it is the superimposition of a rectilinear flow parallel to x-axis and the doublet. That means here if we see that there is a rectilinear flow parallel to x-axis, if you take this as x, this as y, this is u. So stream function for this rectilinear flow uy we have already discussed, and this is the stream function for the doublet. So if you superimpose a rectilinear flow with the doublet, then what you get, uy plus c as defined earlier for the doublet sin theta by r. Now if I write y in terms of r and theta in polar coordinate system, so it will be r sin theta plus c sin theta by r. This is the typical stream function for the combination of rectilinear flow parallel to x-axis and the doublet. Now you see that in this type of stream functions we get some interesting thing, that at psi is equal to 0, that means if we consider one value of the stream function arbitrarily to 0, that means along a streamline where psi is equal to 0, we get some conclusion that sin theta is either 0 degree or 180 degree. That means if sin theta is equal to 0 and 180, the value of stream function is 0. We can ascribe the value of stream function to be 0. Another solution is that for any theta we can get a value of psi 0 provided ur is equal to c by r, or simply r square is c by u, or r is equal to root over c by u. Let this root over c by u be denoted by a. That means for all values of theta, psi is equal to 0 is obtained along points whose radial coordinate r or radius vector r is constant, because c is a constant for the doublet and u is the constant because rectilinear flow the velocity u is constant, which is parallel to the x-axis, so this is constant. So if you replace now mathematically root over c by u is equal to a, then we get psi is equal to minus u sin theta into r minus a square by r, because c is a square u, minus u sin theta r minus a square by r. So this is the streamline which is obtained. Now if you write this streamline again, that